Hello everyone. So now we are going to solve the Poisson equation for a simple case, right, of a heat flow in a one-dimensional or special space. So here, let me just kind of brief you what we are going to do here. Just imagine now we have a source on the right hand side, which is here. So you have a source which is at 100 degrees Celsius, and this source is going to be then you just imagine you have a very tall item, right? For example, your refrigerator. Okay, and then you have on this side, let's say you have a wall, right? And here at the wall, let's say the temperature over here is 0 degrees Celsius. So now this is going to be a very tall wall as well, and so you are not going to consider the y, but then you are just going to consider the dispersion, the diffusion of the heat, right? The heat flow from the right here, that is your refrigerator or your source, towards the left hand side, right? So your heat is going to go this way. So now we are going to solve this, and let's look at the first step that we need to do. So now to solve the Poisson equation, we must first look for the solution of a steady state. So in this case, there is no dependence on time, and you are away from the source. And you have this equation that looks like what you have seen before, and this is your Laplace equation, right? Now in this equation, the problem that we are considering now is actually a 1D case. So since this is a 1D case, your del operator is going to be dependent on x only. Okay, so if you're considering a 2D case, then you have the y or a z term. Now we have this equation that we want to solve, and here you can see that the function u that fulfills this equation is linear with respect to x here, because if you have x squared, and then you will see that this is not true anymore. Okay, so here you should satisfy yourself by putting u equals to ax into the equation, and you can easily show that this is exactly 0. And so what we have done now is to actually find a general form for u, right, at a specific time. So this is actually the solution at time t equals to 0. So now at time t equals to 0, at x equals to L here, so this is our heat source, right? So our heat source is over here. So if you use this equation, u equals to ax, and you replace at x equals to L, then your u is equals to 100, and then you will determine what is a. So in this case, a is equals to 100 over L. So this is going to be the solution, the first solution that you want, that is u naught equals to 100 divided by L multiplied by x. And we will see that later on, when we have the second solution, we will actually combine them, and then we will use it to determine the Fourier coefficients. So now the second step is that we want to find a solution for the spatial part for t larger than 0. So what we have done in the first step was to actually determine, the solution when you have t equals to 0. And now in the second part, we want to find the solution when you have the heat flow when t is larger than 0. Okay. Here if you have looked at the first video of this series, you will actually come across a general solution for the Poisson equation, and you have already see that we can actually separate it into two terms, and the first term, which is f over here, is dependent only on the x variable, and then you have a second term, which is the exponential term, and this is where your dependence on time comes in. And you can also see that this fx has been determined. The general solution has been determined, and we can see that this equation that fulfills this the function that fulfills this equation is of the form sine kx and cos kx. So from these two functions, we will use the boundary condition to select and to remove one of them, right? So at x equals to 0, we have the function to be equals to 0 because the temperature at x equals to 0 is 0, right? Therefore, we will just simply put in x equals to 0 over here. So you have a sine k multiplied by 0, so sine 0 is exactly 0. So this solution is the one that we want. On the other hand, the fx equals to cos kx, if you put x equals to 0, you will see that cos 0 is equals to 1, and this is non-zero, right? So this is not equals to 0, and we do not want this solution. So now we have retained the sine kx as our solution for the spatial part, and we consider next the second boundary condition, that is at x equals to L, and then we want to have fx equals to 0. So now this might look weird to you, but we have to decide this, based on the problem that we want to solve. So in this case, we have a heat source at x equals to L, and we actually assume that over time, the temperature at this point is going to drop to 0. So it's going to start off at time t equals to 0, we have 100 degrees, and then as time goes on, the temperature is going to decrease to 0. So now with this boundary condition, we put x equals to L over here, so you have sine KL, and this is going to be equals to 0, and from there you will determine what is k, right? So now in this case, k equals to n pi over L. So the solution for the spatial part is like this sine function. But if you remember from the lecture on the Laplace equation, you will see that the sine function alone is not able to fulfill one of the other boundary condition, right? So what we do is we take a Fourier series. Okay, so we take a series where we have the combination of sine function with different n. So the general solution now is like this. So you have a u, which is a temperature to represent temperature, x and t. So this is written like this. You have a summation n equals to 1 from n equals to 1 to infinity. So Bn is the coefficient, the Fourier coefficients that you want to determine, and here you have a sine function which you have seen, and also now this is the exponential alpha k squared t, right? Okay, so the next step is to find the Fourier coefficients. So in order to find the Fourier coefficient, you have to put t equals to 0. You put t equals to 0, and in this case, right, at time t equals to 0, you want the temperature, which is your u x t, but t equals to 0, so you have u x 0 to be equals to the steady state solution. So you want to have the initial solution here, right? So you want to equate the temperature u to be equals to the initial solution. So the initial solution, if you remember, u naught is linear with respect to x. So what you do now is to actually put u naught, which is 100 over lx, and on the left hand side here, this is your sine function, right? So now you have to just do the usual steps to determine what is Bm. So you multiply both sides by a sine function. So when you multiply the sine function here, and you will have a case where n is equals to m, so therefore this is going to cancel the summation sign, and then you will integrate over all x dx, right, over all x direction. Then I put a triple dots here to just to tell you that there is a long derivation involved, and this is the one of the step that you should get. And then you follow up a little bit more, and finally you will have the coefficients Bm equals to this expression, right? So here now Bm or n, this is the same. You can use interchangeably between m or n, but the most important thing, this is the form that you want, right? So if you look at this, you have a sine function and the cos function. So if you put m equals to, let's say, 0, for example, so if you put m equals to 0, sine function is going to vanish. Well, this cos 0 is going to be 1, right? On the other hand, here you have sine 0, 0, so you have only contribution from this part. So what you have is at the end, if you have m equals to 0 or even numbers, you will get this term equals to negative 1 here. So therefore you can write it like in this form. On the other hand, if you have odd numbers for m, then you will see that this whole thing is positive. So you will have these two solutions, right? Then in order to kind of like write it in a nicer form, you can write the coefficients to be equals to 200 over pi, which is over here. This is obtained from here. And then you have a negative 1 m minus 1 divided by m. So m here comes from this term over here. And on this negative 1 to the power of m minus 1 is obtained in order to take into account the effect of even or odd numbers, right? So if let's say m is equals to 1, for example, m equals to 1, so negative 1 to the power of 0 will give you 1, right? So you will get this 200 over pi. Right, so this is the solution that you want for the heat flow. So we have seen the first step. What you need to do is to find the solution for a steady state. Just recall Laplace equation. And second step is you want to find a solution that fulfills the Poisson equation for time larger than t larger than 0, or any time that that you want to have the heat to start flowing. And finally, you will see that you have these two solutions. So now you want to find in the third step the Fourier coefficients. And in order to find the Fourier coefficients, you are going to equate at time t equals to 0, t equals to 0, so that your exponential term is going to be equals to 1. You have on the left hand side the term which is related to the sine function together with the Fourier coefficients, and on the right hand side you have your initial solution, initial equation, right? And then from there you will determine what is your coefficients, and after that you have the full solution. Alright, so this is the function u representing the temperature from the heat source to the wall. So we have actually found how to get the Fourier coefficients earlier, and we have seen sine kx and exponential term which is related to t and how it appears in this equation. So let us recall what we are discussing about. So we are looking at the source on the right hand side here. So the source is over here and it supplies 100 degrees Celsius, the temperature here, and at t equals to 0, right? So this is at t equals to 0. So when you kind of like start the count, right? You start the count for t, and then you have the flow of the heat from the right here to the left. Okay, so you go from the right to the left, and as the heat goes in this direction, the temperature now over here is going to drop to 0. So it depends a lot on what kind of a problem that you are trying to solve, right? So in this case, we are looking at a situation where you have a flow of heat, and then here this area is going to cool down as a function of time, right? Okay, so so now what we want to do is to plot this, and in order to plot that, we must provide into the plot some values actually. So one of them is the heat transfer coefficient alpha here, and then we must know what is L. So in this case, the L, we are taking it from L equals to 10, right? So L equals to 10 over here, and the point here is x equals to 0. Okay, so then of course we must have n. So n is going to change from 1 to a value that we want. So in this case, we are going to take from n equals to 1 up to 10. So let's look at the plot. So now to plot here, I have put alpha equals to 1. So we will just take 1 as just for a trial value, and L equals to 10 as we have mentioned, and the increment for the n is going from 1 to 10. And now we need to define our t, which is the time. So here we take t equals to 0 to 50. Then now x is going to be slightly slightly confusing maybe, because now what I do is I take x to be going from 1, sorry, this is not 1, this is L, going from L to 0, so it's the other way around. Okay, so if you remember from the plot just now, from our figure, our sketch just now, we have 0 to L, right? So now the heat is going from L to 0. Okay, then I make a mesh point from these two quantities. So now we are ready to plot the function u. So before that, we have to define u equals to 0 first, because this is a sum. So we must make sure before you enter the loop, you have to have u equals to 0. So now we can do a loop now. U going, that is I going from 1 to n. So n is 10 here. So then I will calculate k, which is n pi over L. So now I replace, instead of n, I replace by I, and I is going to go from 1 to n. And now I'm calculating u, k. Okay, yeah. So this is the equation that I wanted to show first. So now I'm going to plot this using the mesh points, right? So tt is defined in these mesh points. And then I'm going to close the loop now. And now I'm ready to make the plot. So now I'm going to make a mesh plot, right? So this is as a function of x and t, and this is the temperature. So now when I plot that, this is the temperature distribution that I have. So the heat is from here, it is from here, because this is x equals to 10, t equals to 0, and then it's going to have it's going to spread out over x and t. Okay, so this is the mesh that you get if you plot using the mesh points. Okay, but that is a more meaningful thing, because what we wanted to see is the direction of the distribution. Okay, the distribution of the temperature as a function of space, right, your x, at the given time. Okay, so we can do that, right? But not in this way. So let's close this. So what we do now again is to define u equals to 0 again. So we define u equals to 0, and then now we start again our loop. And the k, of course, we have to calculate the k, and now I calculate the u, but instead of calculating it at the mesh points, I'm going to actually calculate at the points that I have actually inserted above here, right? So my x is going to take from L to 0, and the t is going to go from 0 to 50. Now I can end the loop. Okay, so now we are ready to plot. So let's plot first the temperature u here as a function of x, right? So then you will have something that goes like this. So this is, again, this is the source over here. So the source is over here at time t equals to 0, and then you have a distribution of the temperature as a function of x. Okay, so you have a nice curve like this. So the maximum appears to around this x equals to 9, but this is depending on the alpha value that you give, right? So the heat transfer coefficient. So the different heat transfer coefficient is going to give you a different distribution, and you will see that if you change your alpha to a larger value, the peak is going to shift nearer to the heat source here. Okay. Now I want to show you another plot. That is, we want to plot this as a function of x and t at the same time, right? So we will use plot 3 xtu, right? So position, time, and the temperature, and then you have a plot that looks like this. So this is not too clear, so what I will do is I will just put the grid. So I'll put the grid on, and then you will see this, right? So this is the x and this is the time, the t axis, right? So here you see, so you start from this is your point source, not point source, sorry, the heat source, and this is you're going to have a heat distribution as a function of time. Okay, so you see the peaks over here. Okay, so here you actually calculate the x and t at a given time, right? So this is very interesting, because now you see the distribution, the flow of the heat as a function of time, and at the given point, at the given point in time, this is where it is in the temperature at each x. Okay, right. So now let us try to change the value of alpha to see how does it change, right? So let's consider alpha equals to 5, right? We increase from 1 to 5, and then we are going to again we are going to use the same x and t values. So we are now ready to replot our data. So again we have to calculate k, and now I will calculate my u. Okay, and this is to close. So now I will plot both the time and the position together, and then you will see a sharp curve, right? You see there's a sharp curve. So maybe let me just put the grid minor on, and here you will see by changing the alpha value from 1 to 5, there is a drastic change in the heat distribution. So here you have a peak of the temperature at close to the source, right? So initially it was around here in this region. So now when you shift from 1 to 5, the alpha from 1 to 5, then the maximum heat is over here. Okay, right. So yeah, so basically this is the plots. We have actually look at the plots of the function that represents the temperature due to the flow of the heat from a source as a function of a one-dimensional x coordinate and time, right? So I hope this has been fun for you, and that's all from me this time. So thank you very much.